Hopefully I'll make no typos in the sheet. Okay, so these are called the sum, difference, and co-function identities. So if I gave you something like cosine of x minus y, don't write this down, just watch. Your first thing that you really, really hope happens, you really hope that's equal to cosine x minus cosine of y, right? Like that would be really easy if that was true, right? But if you try certain numbers, let's say you could try x equals pi halves and y equals pi quarters. This would be cosine of pi halves minus pi quarters, which would be cosine of pi quarters, right? Which is root 2 over 2. And this would be cosine pi halves minus cosine pi quarters. That would be, what's cosine of pi halves? I think it's 0, right? Right there? Sine is y, cosine is x, yep. Do you see how you get something that's not actually equal? So the moral of the story is that no distribution of trig functions. And that's not the first time you've seen things that don't distribute. If you had x plus y squared, does that power distribute? No. If you have 1 over x plus y, can you break that into two fractions? No, you can't break it into 1 over x plus 1 over y. So it's not the first thing it doesn't distribute, but the sad thing is it doesn't. Here is what it simplifies to. That. Okay, observe the craziness. So if you have cosine of x minus y, it's equal to cosine x times cosine y plus sine x times sine y, which seems a little bit bonkers, right? That's a pretty complicated identity. So what I'm going to actually do is show you where that one comes from. And we're going to talk about how to use it. So your book explains this, and it's actually not terrible. But I think it's better if somebody tells you what they're talking about. So draw a circle as best you can. Nope, we're on the new one, but yeah. Yep, it's all good. Okay, I'm going to call this angle x. I'm just going to assume x is in quadrant 2. And I'm going to call this angle y. Okay, the point where I'm going to have those 2 points where my rays intersect the unit circle. So I'm going to call this point B. It's going to have coordinates, we're going to call them C and D. Does it make sense that C will be cosine of y and D will be sine of y? Remember that when you're on the unit circle, cosine is, the x coordinate is cosine of the angle, the y coordinate is sine of the angle, right? And I'm going to call this point A, and that point A will have points A, comma, B. And what are its coordinates going to be? So think about it. B was cosine y, sine y, right? What is the angle at point A? X. So this will be cosine of x, sine of x. Those are the coordinates there. Okay, now the angle between them, like this part, does it make sense that that's x minus y? That's how many degrees it is, or radians or whatever, but that's how big the angle is x minus y. So what I'm going to do is I'm going to take that angle and I'm going to shift it and draw it over here. So, and that's going to have the sort of exact same sort of distances and stuff. And I'm going to call that point C, and we're going to call it E, comma F, because those are the next letters in the alphabet. And that will equal cosine of x minus y sine x minus y. So the point that the book uses, the reason they use the letters A, B, C, D, E, F is because they're a lot easier to work with than the cosines and the sines, so we'll just simplify this stuff with those letters and we'll go from there. All right, so here's the thing that you're going to use. Does it make sense that the distance from A to B is equal to the distance from this point right there, which is the point 1, 0, to that point C? Does that make sense? That's got to be true. So how far it is from A to B has to equal how far it is from C to E. So just all I did was took that angle and just moved it over, right? Do you remember how to find distances? That was that square root formula. Square root of x2 minus x1 squared. I tried very hard to make you memorize it, and you all resisted me. So we're going to use that, okay?
Well, I didn't have to memorize it because it was just pathetic.
It's the there was also that, right? Okay, so we're going to use this. So first of all, A to B. So the points for A are A comma B, and the points for B are C comma D. So that'll be the square root of, let's see, do the same order, C minus A squared plus D minus B squared. That's the distance from A to B. Say that a little bit louder.
You're just plugging it in.
I'm just plugging it in, yep. So in for this formula, I'm plugging in what x and y are. Does that make sense? And x2, we'll just think B is the second coordinate, right? B is the second point, A is the first point. And on the other side, it's from that point C to 1, 0. So I'm just going to take 1, 0 to be my x2 for some reason. That's just the way the book did it. So that would be 1 minus e squared plus 0 minus f squared. And those C, D, B's, E's, and F's are cosines and sines in disguise. It's just this is a lot shorter to write than any cosine every single time. Okay? So everyone wrote that, just the distance formula?
So that's not the arc distance?
No, it's not the arc distance. It is the straight line distance. Yep. Exactly. Yep, it's not the arc distance. But the arc distance would also be equal. Yep. Okay, now what we're going to do is we're going to square all that stuff out. So here we have the square root of, actually, not that. First we're going to get rid of those square root signs. We've got 2 square root signs, right? So what can we do to both sides? How would you get rid of the big old square root sign? Square it, right? So you're going to square this side, square that side, and we end up with C minus A squared plus D minus B squared equals 1 minus E squared plus F squared. And now we're going to do massive, crazy expansion. It's like if you take C minus A and you square it, and Dane, pay attention because you've messed this up a couple times, okay? So C minus A squared, when you square C minus A, what do you get?
E squared
Minus
AC.
Minus how many ACs?
2AC.
2AC plus A squared. And then we'll have D squared minus 2DB plus B squared equals, on the right side, 1 minus 2E plus E squared plus F squared, right? Okay. Is everyone okay? That's just algebra so far, right? Okay, now we're going to group some stuff together in a clever way. So I'm going to write C squared plus D squared. I'm going to write A squared plus B squared minus 2AC minus 2DB equals 1 minus 2E plus E squared plus F squared. Whoa, 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 don't you dare. Okay.
Panic.
I already had this happen once today. I don't need more technical difficulties. Is everyone okay with what happened there? Okay. So here is why that's helpful. Remember that the C's and the D's and the E's and the F's were actually sines and cosines. So like this part right here, C squared plus D squared, that's cosine squared plus sine squared. Does that make sense? So what's that going to equal? That's going to equal 1. That A squared plus B squared, that is cosine squared x plus sine squared x, right? That's also going to equal 1. Minus 2ac minus 2db equals 1 minus 2e. What do you think about e squared plus f squared? Also going to equal 1.
Can you write out the c squared plus d squared? Or there's just one?
I can write out one of them, yep. So c squared plus d squared, that is, so c is cosine of y, d is sine of y. Does that make sense, Donnie? And so therefore that's going to equal 1. As true as long as the points have the same variable inside of them.
The same variable.
Does that make sense?
Yeah.
The other one, the a squared plus b squared, that's going to be cosine squared x plus sine squared x. And the final one is just going to have x minus y inside both of them. Okay, but that identity is true as long as the variables are the same. If I gave you cosine squared x plus sine squared y, then it's not true anymore. Yeah, do you have a question?
It's not supposed to be minus 2e squared.
That should be just minus 2e. There should be no e squared. Do you guys agree with that?
Mm-hmm.
Okay, great. Thank you, Charles. Okay, so now we have 2 minus 2ac minus 2db equals 2 minus 2e. Is everyone okay with that? Just added the ones together. What happens to the 2's?
Distribute.
No, even easier. If you try to combine like terms.
Oh, yeah, because every single,
So you
everything has
take away 2, what happens to those 2's? They disappear. You get negative 2ac minus 2db equals negative 2e. Now couldn't you divide, and it'd be doing better, divide the whole business by negative 2, right? And you get ac plus db equals e, right? And the last thing to do is fill in what a, b, and c are in terms of sine and cosine. So what is a equal to in terms of cosine? A is cosine of x. C is cosine y. So that's cosine x times cosine y. D is equal to, B is equal to sine x, right? And E is equal to cosine of x minus y, right? So complicated Pythagorean theorem is why this is true. I couldn't have proved that without my notes, okay? Like, I'm not going to make you do this, but this is not just magic is my point, right? There are reasons why this is true, and it has to do with distances. And the fact that that Pythagorean identity is true, that sine squared plus cosine squared is equal to 1. Does that make sense? So all we're going to do now is we're going to use this formula, okay? That's it. So you don't have to memorize it. We're just going to have to, if it's on a sheet, you're going to have to use it. And I'll tell you to use your identity sheet and blah, go, okay? So let's do a few problems where we use it. So it's on your page. I'm going to write it down. It was cosine of x minus y equals cosine x cosine y plus sine x sine y. So in the case of this problem, what are we plugging in for x? But it's not a trick question. X is the first thing, right?
Yeah.
So you plug in x for x, okay? The minus sign is built in as part of the formula. So what do you plug in for y?
It's pi.
Plug in pi for y. Gesundheit. So cosine x minus pi will be cosine x times cosine pi plus sine x times sine of pi. And then just simplify as necessary. Can you work out what cosine of pi is? It's that point right there. Cosine's which coordinate? The x, that is the point -1, 0. So what is the cosine? -1. So that's cosine of x times -1 plus sine x times, what is the sine at pi? 0. So what is anything times 0? 0. So I believe this is just negative cosine of x. Okay. What that tells you is if you were to graph cosine of x and cosine of x minus pi, they're going to be the exact same picture. Does that make sense? And that should make sense because these cosine curves, they have this repetitive pattern, right? So you can theoretically reflect and shift the curve back onto itself. Does that make sense? So that's what, if you want to check if you're right, you could actually do that by like using a graphing app and graphing both of them and seeing if they produce the same picture. Okay? Try the next one. Oh, the next one's a little bit tricky. Okay, so why is the next one a bit tricky? What did our formula have in the middle?
Minus.
It had a minus. So here's how you make this have a minus. You're really clever because you're watching like Doctor Who, so you use the word clever. You make it x minus -3 pi over 2. Does that make sense? And that trick comes up in calculus all the time, so it's a good one to know. So what you plug in x for x. What do you plug in for y in your formula? -3 pi over 2. There is a formula for plus, and we're going to have it on the next page, but you don't actually need it as long as you know this trick. So this will equal what? Cosine x times cosine of -3 pi halves plus sine of x times sine of -3 pi halves. What's the equivalent positive angle to -3 pi halves?
Pi halves.
Pi over 2. Yep, so it's this one right there. That's backwards 3 pi over 2 is the same as forwards pi over 2. So at that point, the coordinates are what? 0, 1? It's really easy to be dyslexic with those things, right? Gosh. So that's cosine of x times, what is cosine of -3 pi halves? 0, great. Plus sine of x times 1. What's up, Tani?
So cosine x times,
So
0 is a cosine times -3 pi.
gets cosine, when you plug -3 halves into cosine, you get out 0. So I think that's just sine, isn't it? So if you take your cosine curve and you shift it left 3 over 2, you've changed it into a plain old sine curve. Okay? All right, awesome. So you can use these sum difference identities to get these things that are called the cofunction identities. That's what example 2 is. It's called a cofunction identity. So we're going to find an identity for cosine of pi halves minus y. Okay, so cosine of pi over 2 minus y. So that will equal cosine pi over 2 times cosine of y plus sine of pi over 2 sine of y, right? You buy? Okay. In your head, visualize a unit circle. What is cosine of pi halves?
0.
0. What is sine of pi halves? 1. So this equals sine y. So that's an identity. Cosine of pi over 2 minus y equals sine y. Okay, and we're going to use that to get a different sum difference identity. And that's the thing on the next page. So is everyone okay with it? This is true? Okay. So what we're going to do is we're going to take this identity that we found in example 2, which was cosine of pi over 2 minus y equals sine y. Okay, so we're going to use this. So that's from example number 2. We're going to plug in this for y. Okay, so we're going to take y equal to pi over 2 minus x. And the only thing you have to do is be really careful when you input this that you put it in parentheses. So when I input this for the y, the right side's pretty easy. What is the right side? Sine of, well, it was, you're replacing y by pi over 2 minus x. So everywhere there's a y, you now stick in a pi over 2 minus x. So what's on the right side? Sine of pi over 2 minus x, okay? That's what replacement is. You replace something by something else, right? Okay. On the left side, you're going to have cosine of pi over 2 minus, here's a bit tricky, parentheses. If you can remember one thing, inputs always go in parentheses, and you're pretty much never going to be wrong if you do that. I can't think of an instance you will. And why are those parentheses so important on the
negative distributes.
The negative distributes, yep, and that becomes cosine of pi halves minus pi halves plus x, right? Oh man, which just becomes what? Cosine of x. Do you see that we've kind of changed which function has the pi over 2 minus x inside of it there? So with the first one, we had the pi over 2 minus stuff inside the cosine, right? This one, we had the pi over 2 minus stuff inside the sine. And the thing that we're using here is that when something is an identity, it works as long as this thing matches that thing, even if the matching thing is some weird expression. Does that idea make sense? Okay, so your y can actually be, it could be 5,720, 5,250. It could also be pi over 2 minus x. Okay? And we're going to be able to use this to get an identity for sine of x minus y. So how? Okay, so the thing that we just found was that cosine of x equals sine of pi over 2 minus x. And the other one that we found was that sine of x equals cosine pi over 2 minus x, right? Those two? Once again, don't have to memorize those, okay?
Wasn't it cosine pi over 2 minus y?
Does it really matter?
Oh.
Does that make sense though? But you're right, I did have it written as sine of y equals cosine pi over 2 minus x y, but does the fact that I use y versus x really matter at all? Doesn't really, because you can just replace x by y, right? Okay. The reason that I used two different variables was so the substitution we did to get the second one was a bit easier. So we're actually going to use this one, and we're going to start with sine of x minus y. And we're going to plug in the x minus y for the x. So that will equal cosine of pi minus the quantity x minus y. Oh, pi over 2, sorry.
The pi over 2 is coming from the previous problem?
The pi over 2 is coming actually from 2 problems ago, but
Oh.
yes. It's coming from this identity. And I plugged in x minus y for x. Just replaced x by x minus y. And then this is your first thing, that's your second thing. You have an identity for cosine, right? This is, oh shoot, that's not right. I'm so sorry. I need to look at my notes before I do this. Distribute that negative. Make this cosine pi over 2 minus x plus y. We're going to change the grouping. And this is cosine of pi over 2 minus x minus negative y. So think about those two things as your first thing. This as your second thing. And we're going to use the cosine formula from the previous page. Okay, so this will be cosine of first thing times cosine of second thing plus sine of first thing times sine of second thing. That is the formula we got from the first page, the very first one we did with the Pythagorean theorem. It's just that we're plugging in this pi over 2 minus x and the negative y. That's the whole cosine x, cosine y, plus sine x, sine y formula. Okay, that's all we did. Does that make sense? Okay. Now here's where it gets a teeny weeny bit tricky. What was cosine of pi over 2 minus x equal to? It's on the top of this page.
Sine.
It's equal to sine. Cosine of negative y is one of those, don't you be fussy. What are you initializing? Stupid. Seriously?
My charger likes to say that when I
Can
plug
I
it
beat
into my
OIT?
phone, it says it's not compatible with this device even
I-
though it's
I-
charging.
what? Okay, I pause this. I got sine x, cosine y, plus cosine x, negative sine y. All right, and then what's the last thing? How about making it sine x, cosine y, minus cosine x, sine y? Does that make sense?
Yeah.
Just multiplying the negatives together instead of making it a plus, making it a negative. So the basic point is that everything comes from this identity and these cofunction identities, and those came from this thing, right? Okay, so you can prove them using that thing. It's really, really complicated, and here's your list. See, big list. Ready? And so you're not going to have to memorize them, you're just going to have to use them. Does that make sense? We didn't even bother to try to prove the one for tangent, but there it is. So I don't know how to do it off the top of my head, but I'm sure we could figure it out. Now the kind of cool thing about this is it lets you find sines and cosines that you could not otherwise find exactly, as you'd have to use a calculator. So for example, 75 is not a number on your unit circle, right? Can you express 75 as a sum of two numbers that are on your unit circle, though? So we have like 30s and 45s. Does that make sense? So the trick here is partially figuring out what to express this as, but this is the same thing as tangent of 45 degrees plus 30 degrees, because 45 plus 30 is 75, right? So part of it takes like figuring out like what two things should I add up, and I would say if your number ends in a 5, I'd suggest subtracting 45 and seeing what's left over, And maybe it's those two sum of things that you're going to use. So then look back at the previous page.
Yeah, any multiple of 15 will work.
Yeah, except for you don't have a specific formula for 15, right? So the formula for tangent is that tangent, because I don't memorize either, tangent of x plus y is tan x plus tan y over 1 minus tan x times tan y. So how are you going to use that to figure this out? What's going to go in for x? And what's going to go in for y? 30. So that will be tangent of 45 plus tangent of 30 over 1 minus tan 45 times tan 30. Okay, so there's 45, here's 30, there's 60. The coordinates at 45 are one of the easiest, right? What are the coordinates at 45? They're both root 2 over 2. How about this first one? Root 3 over 2 and a half. Okay. So if you're asked to find tangent of 45, what's it going to be? 1 plus tangent of 30. Tangent is sine over cosine or y over x, right? So that will be 1/2 over root 3 over 2. Shouldn't I be using negative 30? Why?
Because it's tangent of x minus y.
Oh, but there's a formula for tangent of x plus y as well.
Oh, I didn't see that one.
Does that make sense?
Yeah,
Mhm.
totally.
Yep, but you can memorize just one and just do what you said, and that would be fine as well. Yep. Over 1 minus tangent of 45 is 1 times, hey, what is 1/2 over root 3 over 2 going to be anyway? At least initially. 1 over root 3, does that make sense? At least that much. So I've got 1 plus 1 over root 3 over 1 minus 1 over root 3. And that's okay. It's a little rude to leave fractions in fractions, but at least that's a start. Okay, so what could you do from there to simplify this just a little bit more?
You can multiply by the reciprocal.
Yes, by which I think you mean multiply by root 3.
Mhm.
Does that make sense, guys? That's going to help you a little bit. That's going to cancel out the denominators that are root 3. So this will be root 3 plus 1 over root 3 minus 1. I think there's enough stuff in that problem, but Alex is going to make you rationalize the denominator. And it's also going to be on your final to do that, so it's probably good to review it anyway. So what do you multiply by to rationalize that denominator?
Root 3
Root 3 plus 1 over root 3 plus 1. That was ages ago, but we did do that, right? So I think that's, what's root 3 times root 3? 3. Root 3 times 1 will be root 3, plus another root 3 plus 1, over 3 plus root 3 minus root 3 minus 1. The reason you chose that thing to be the same numbers but opposite sign in the middle for the denominator is because you then have that pattern where those two middle things cancel out. Does that make sense? If those two things don't cancel, you chose wrong. So I think this is 4 plus 2 root 3 over what? 2. Divide by 2 and you get 2 plus root 3. I apologize for the tedium. So. The next one's actually a bit easier. The tangent one was just hard because you got a fraction, so you have to often rationalize those denominators. Okay, and then so that one involved a sum. 15, you can't sum it as two obvious angles. Does that make sense? So probably going to use a difference. Does that make sense? So the kicker here is you'll use the fact that this is sine of 45 degrees minus 30 degrees. It's actually not the only combination you could use, but you know, it works. Okay, so then look at your difference page, the formula there for, I think I actually derived it, sine of x minus y is sine x cosine y minus sine x sine y. Nope. Nope, nope, nope. That's wrong. Minus cosine x sine y. Yep. Yep. Okay. So in this case, what goes in for x and what goes in for y?
45 for x.
30 for y, right? So that'll be sine 45 cosine 30 minus cosine 45 sine 30. All right. So what's sine of 45 degrees? Mm-hmm. Cosine 30 is root 3 over 2, right? Cosine's the x, yes? Okay. Minus cosine of 45, which is still root 2 over 2, right? Times sine of 30, which is 1/2, right? So that's root 2 times root 3 minus root 2 all over what common denominator? 2 times 2, which is 4. Here's the two best ways to express this. Either factor out the root 2. Does that make sense? And nothing else cancels, right? It's just a disgusting angle. Or write it as root 6 minus root 2 over 4. That's also fine. How did you get root 6? Where the heck did I get root 6? The 2 and the 3. Multiply roots by roots, that's totally okay. Yeah.
Isn't the x value for 30 degrees 1/2?
It's not, yeah. So if I drew this a little bit better, this is a 30-degree angle.
But in the last problem, we used 1/2 for the x value.
No, we didn't. In the last problem, we did tangent of 30, and that's sine 30 over cosine of 30. So what we did definitely do 1/2 over root 3 over 2. Yeah. But I mix them up all the time, so it's good to at least question me to make sure. Yeah. The way you can tell what's what is that root 3 is bigger than 1. So that side is obviously longer than this side. Does that make sense? So that's how I tell that that first one's got to be root 3, because the triangle is obviously bigger along the horizontal side. That's my personal preference. My friend Bob remembers that the numbers go 3, 2, 1, 3, 2, 1. You see what he sees? That they go 3, 2, 1, 3, 2, 1. I mean, that's his trick. So, whatever works for you. But yep. Okay, awesome. So we're going to do a couple more examples. We'll do one identity. So find the exact value of cosine of x plus y, given that you know sine of x and you know cosine of y, and you know that x is an angle in quadrant 2 and y is an angle in quadrant 1. So I went through and I was like, oh, woohoo! There's a formula for cosine x plus cosine y. It's cosine x, cosine y, minus sine x, sine y.
So will you give them a sheet of some of the,
Oh my gosh, yeah. That thing that's boxed on page 2, you will have a sheet that contains the contents of that box.
okay.
Okay? As in, like, so when you're doing Alex and stuff, use them. Okay? If you memorize them in the meantime, whatever, right? It's good. So what parts of this do you already know? Put check marks by them. What were you told?
Sin x and cosine y.
You know sine x and you know cosine y. Does that make sense? You were told what they are. You were told that sine x is 3/5, and you were told that cosine y was 4/5, right? Okay. And you were also told what quadrant they were in. So x is an angle in quadrant 2. So sine x equals 3/5. That x is an angle over here. And remember that another way to define the sine was by saying, oh, sine is the y coordinate of that triangle over the hypotenuse. So in that triangle, this is 3 and this is 5, right? Vertical distance over the hypotenuse. It's just the unit circle, the hypotenuse is already 1. How would you find that missing side? Pythagorean theorem, and I think it'd be, yeah, it's gonna be 4. It's a Pythagorean triple, but it'd be 3 squared plus b squared equals 25, right? Or 5 squared. Okay, so there's one of them. And actually, from that picture, now can you find cosine of x?
Yes, you can use the triangle.
You can use the triangle, and the one tricky thing is that will cosine be positive or negative in that quadrant?
Negative.
It'll be negative. The x side is -4 because you went backwards, right? Over the hypotenuse, which is 5, okay? So now you've also found that part. How do you think you're going to find the one remaining one? We did a triangle there, right? Any reason not to do it again? Using the fact that sine of Using the fact that cosine of y is 4/5. What angle was what quadrant was the y angle in?
Quadrant 1.
Yes,
On the top right, did you write a B or a 6 squared?
that's a B.
Are we using A's and B's? Where does B relate to?
It's like a squared plus b squared equals c squared.
No, sorry.
It's all good. Yep, no problem. Okay, so for this angle y that's in this quadrant, cosine gives us which side of the triangle, horizontal side or the vertical side? Horizontal, and how about this other side? What is it going to be? How is the hypotenuse going to be? 5. What's the other side, missing side, going to be then? It's the exact same as the other triangle, isn't it? It's going to also be 3. So using that, what is sine of y going to equal? 3/5. Awesome. Okay, then just plug in what you know. Cosine of x, that is -4/5. Cosine y is 4/5 minus sine of x, which is 3/5, times sine of y, which is 3/5. So that's -16 over 25 minus 9 over 25. What is -16 minus 9? -25. And that simplifies to -1. Awesome. Okay. All right, and the very, very last thing we're going to do in this section is show an identity is true using these formulas. So I might ask you to do this, but you would once again be given the formulas to work with. So here's the last one on this notes. So it's a little bit not obvious which side is more complicated here, but I would say it probably is a good rule of thumb to try to get rid of subtractions and additions inside a cosine using those formulas we have. So we're going to start with the right side and work our way to the left. And I think cosine of x minus y was the first one we did, right? Okay, so that's going to be, what was it, cosine x, cosine y.
Plus sine x and sine y.
Yep. All over cosine x sine y.
Wait, the line go all the way past that?
Yeah, yeah. Is everyone okay with that part? Can we cancel anything immediately? Why can't we cancel the cosine x's? And also it's only in the first term, not the second one, right? So what you can do, we didn't actually see this trick yesterday, is you can break it into two fractions. Write it as cosine x cosine y over cosine x sine y plus sine x sine y over cosine x sine y. Does that make sense? It's kind of like if you have a third plus a third, that's 1 plus 1 over 3, right? It's the same thing, just in the other direction, right? Usually we add fractions, keep the common denominator. Now we keep the common denominator and unadd the fractions. So now, can you simplify anything in the first fraction?
Yes.
Yeah, the cosines can cancel. So you've got cosine y over sine y. And the next one you've got sine x over cosine x, right? And isn't that pretty much what you need? What's cosine y over sine y?
Cotangent y.
Cotangent y. The fact that they're both y's does matter, right?
Yeah, if it had like.
If you had a y and an x, there's no identity that simplifies them. Well, there might be one, but it's not that easy one. And what's sine x over cosine x?
Tangent 1.
Tangent of x. And is that what you had to prove?
Yes.
So make a big box. That's your, like, I proved it. Okay, well, with technical difficulties and stuff, well,